Welcome to the new concept of natural gas transmission under the edges of chemical process utilities. Now, before we go into the detail, let's have a brief outlook about that what we studied in the previous lecture. We discussed about the various elements of pipeline design. Under these, we discussed about the fluid properties, we discussed about the impact of environment, we discussed about the effect of temperature and pressure. We discussed about the typical flow equations for liquid and gas and gave you an idea about the various codes and standards. We discussed the different societies, those who designed those codes and standards, and apart from this we discussed about the environmental and hydrological consideration. Now, in this particular chapter, we are going to discuss about the natural gas transmission. Here we will discuss the general flow equation in steady state. We will discuss about the kinetic energy term. We will discuss about the pressure energy term. We will have an idea about the potential energy term, and then we will discuss about the frictional loss term. So, let us talk about the general flow equation in the steady state. Now, the general flow equation for compressible fluid in pipeline at steady state condition is usually derived. Now, let us consider a pipeline that transport compressible fluid from point number maybe this is a natural gas from point number 1 to point number 2 at a steady state condition. So, the equation can be written as dm over dt is equal to 0. Now, let us give you an idea about the pipeline. Now, this is the station number 1 and this is the station number 2. Now, here the A1, P1, rho 1 and U1. This is the area of cross section A, P is the pressure, rho is the density and U1 is the velocity, that is a gas velocity. And here this is the A2, P2, rho 2, U2. So, U is the gas velocity, m is the mass of gas flowing, and T is the time for this equation dm over dt is equal to 0. Now, the mass flow rate, the flow rate of gas at point 1, again I am drawing the can be defined as rho 1 A1 U1, and for point 2 rho 2 A2 U2. So, if we from the above equation we can take rho 1 A1 U1 is equal to rho 2 A2 U2. Now, if the pipe has a constant diameter, then obviously A1 will be equal to A2. So, in that case rho 1 U1 is equal to rho 2 U2. So, in general if we say that m is equal to rho A U, now m upon A is equal to rho U, and that is equal to C, where C is gas constant. Now, it is well known that rho is equal to 1 upon U. Now, V is the gas specific volume. Therefore, U upon V is equal to C in this particular equation. Now, from Newton's law of motion, for a particle of gas moving in a pipeline, then dF is equal to A dm, where du over dt is equal to A, that is acceleration. So, dF is equal to du over dt dm or du over dt rho A dy, and that is rho A du dy over dt, and dy over dt is equal to u. Therefore, dF is equal to rho A u du. Now, if by using the proportionality constant Gc, if we use the proportionality constant Gc, so we can write this equation dF is equal to A over Gc u rho du is equal to A Gc u v over du. So, the impact of all existing forces, that is pressure, weight, friction, exerted on a particle of gas in a non-horizontal pipeline, this can be considered in different equation. Now, let us take the forces F1 and F2. This is the F2 and F1 acting on the gas particle due to the gas pressure P1 and P2. This can be defined as dF1 is equal to AD P1 or dF2 is equal to AD P2. So, this is the force acting on particles in a non-horizontal pipeline. Now, the force F3, the force F3 exerted on the gas due to the weight W of the gas particle is F3 is equal to W, this is the angle sine alpha, or we can write in the differential form, that is dF3 is equal to dW sine alpha. Now, where the weight of the gas is dW is equal to GL over GC A dy rho. Now, where GL is local acceleration of gravity. Now, sine alpha is equal to dH upon dy, where dH is the change in elevation on substitution for both dW and sine alpha. So, dF3 is equal to GL over GC A rho dH, or dF3 is equal to GL over GC A over V dH. Now finally, the friction force is defined as dF4 is equal to pi d dy tau, where pi d dy is the surface area and tau is shear stress. Now the summation of all the forces acting on the element of the gas should be equal to 0. So therefore, A upon Gc U upon V du plus A dP plus GL over GC A V over V dH plus pi d dy rho tau should be equal to 0. Now this is the generalized form of Bernoulli's equation. Now in most cases the numerical values of GL and GC, it is equal to 1. Now then if we take this value, then A over GC U upon V du plus A dP plus A upon V dH plus pi d dy rho tau is equal to 0. Now if we multiply both side by V upon A, then 1 upon GC U du plus V dP plus dH plus pi d dy V upon A tau is equal to 0. Now where U dot du is equal to kinetic energy, V dP is equal to pressure energy, dH is equal to potential energy, and pi d dy V upon A tau is equal to friction or losses. The friction term or losses created by moving a fluid in a pipeline is defined by fanning equation, and this is d fanning is equal to 2f u square upon Gc d dl, where u is equal to average gas velocity, F is equal to friction factor, D is pipeline diameter, L is pipeline. Now, if we substitute the fanning equation for losses in the general energy equation, this equation will result like 1 upon Gc u du plus V dP plus dH plus 2F u square upon Gc d dl. This is equal to 0. Now, if we divide both the side by V square, both the sides by V square, then equation becomes 1 upon Gc u upon V square du plus 1 upon V dP plus 1 upon V square dH plus 2F u square upon Gc dV square dl, that is equal to 0. Let us say that this is our equation number A. The final form of the equation can be obtained by integrating each term by assuming u upon v is equal to m upon a is equal to c, and that is constant. So, the kinetic energy term that can be written as integration from 1 to 2 c upon Gc du over v u over v square, and that is equal to 1 to 2 du over v. Since v is equal to u upon c, this can be represented as c over Gc integration from 1 to 2 du over uc, and that is c square upon Gc 1 integration 1 to 2 du u, and that is the kinetic energy is equal to c square Gc ln u2 over u1. Let us talk about the pressure energy term. Pressure energy term. So, it is from 1 to 2 dP upon V 1 to 2 rho dP. Now, from gas law, PV is equal to NZRT. Z is the compressibility factor. The factor of gas, and R is the gas constant. So, N is equal to M upon M and rho is equal to M upon V. The equation for the density for the density of a gas is rho is equal to P m upon ZRT. M is the average molecular weight of the gas. So, if we substitute this into the integration 1 to 2 rho dp, that it becomes 1 to 2 pm upon zRt dp is equal to m upon z average t average r 1 to 2 p dp. This can be 1 to 2 pm zRt dp, that is equal to m z average t average r p1 square minus p2 square upon 2, where t average is defined as t average is equal to t1 plus t2 upon 2. Now, T1 and T2 are the upstream and downstream gas temperature, and P average is obtained based on the relationship 1 to 2 integration P dP, that is P average is equal to 1 integration 1 to 2 P dP upon integration 1 to 2 P dP, and that is P average is equal to 2 upon 3 P plus P1 plus P2 minus P1 dot P2 upon P1 plus P2, where P1 and P2 are the upstream and downstream gas pressures. Now, T average and P average, they are obtained for the gas for the compressibility factor Z average that can be determined from the K's rule and the compressibility factor chart. To calculate the Z average for natural gas using K's rule, T average and average P of the gas are needed, and also pseudo critical pressure and temperature of the natural gas. So, if we talk about the pseudo critical values, this can be obtained by the K's rule, which is as follows: T dash C is equal to T C A y A plus T C B y B plus T C C y C, and P dash C is equal to P C A y A plus P C B y B plus P C C y C plus and so on. Now, where T dash C, this is the average pseudo critical temperature of the gas. P dash C, this is the average pseudo critical pressure of the gas, and TCA, TCB, TCC, these are the critical temperatures of each component, where PCA, PCB, PCC, these are the critical pressures of each component. YA, YB, YC, these are the mole fraction of each component. So, finally, pseudo reduced pressure and temperature can be obtained as T dash R is equal to average T upon T dash C, or P dash R is equal to average P upon P dash C. Now, to obtain the values of TR dash and PR, this can be used in the compressibility factor chart to calculate Z average. Now, this is the compressibility factor chart for natural gas, and you can see Here this is the compressibility factor and this is the pseudo reduced factor. So by substituting the values, you can get the values of either Z or pseudo reduced pressure, whatever required. Now let us talk about the potential energy term. So on integration of the potential energy term of main equation which we derived earlier. So it will result integration 1 to 2 1 upon v square dh is equal to 1 to 2 rho square dh 1 to 2 p m upon zrt square dh, and that is equal to p average p square m square 2f upon average z square average r square average t square into delta h is equal to 0, where delta h is equal to h2 minus h1. Now let us talk about the friction loss term. So if we integrate the energy losses, this can be evaluated as 1 to 2 2f u square upon gc dv square dl. This is equal to 2 fc square upon gc dl. L is the pipeline length. So the general form of the flow equation is obtained by adding all the terms together and equating them to 0. So it is c square upon gc ln u2 upon u1 plus m upon average z average t r p1 square minus p2 square upon 2 plus average p m square 2f upon average z average r T average delta H plus 2 f c square upon g c d l, and that is equal to 0. Now if the kinetic energy term is neglected, for all high pressure gas transmission lines, the contribution of kinetic energy term compared to other terms is insignificant. So we can write m is equal to m upon z average t average r p1 square minus p2 square upon 2 plus p average square m square 2f upon z average square r average square t average square delta H plus 2 f c square upon g c d l, that is equal to 0. Now this equation can be further simplified upon if we take the following assumption or following substitution. C is equal to dot m upon a, c square is equal to m upon a dot m upon a square, and a is equal to pi d square upon 4. Now the gas relationship at a base or standard condition is PB QB is equal to dot NB ZB RTB. QB is the volumetric gas flow. So, if dot NB is equal to dot M upon capital M and C is equal to dot M upon A, then C square is equal to M upon pi D square by 4 the whole square, and C square is equal to 16 QB square M square PB square upon pi square R square TB square ZB square d to the power 4. Now, gas gravity is defined as G is equal to M gas upon M air, where M air is approximately 29. Now, if we substitute and rearrangement to solve QB, then the equation becomes QB square is equal to pi square R GC upon 32 ZB square TB square upon PB square P1 square minus P2 square minus 58 G delta H P average upon RT average Z average upon 58 Z average T average GL d to the power 5 upon F. Now, after taking the square root of QB, the general flow equation of natural gas in pipeline can be QB is equal to pi R GC upon 1856 ZB TB upon PB whole square root P1 square minus P2 square minus 58 G delta H P average square upon RT average Z average 58 Z average T average GL 1 upon F d to the power 2.5. Now, this equation can be used in the imperial or you can say SI units for any size of length or a pipe for laminar or partially turbulent or fully turbulent flow, and for low, medium or high pressure system. Now, as far as the notations are in question, then QB is the gas flow rate at base condition, GC is the proportionality constant, ZB is the compressibility factor at base condition, TB is the temperature at base condition, PB is the pressure at base condition, P1, P2 these are the gas inlet and outlet pressure in the pipeline, G is the gas gravity which is dimensionless, F is the friction factor, again it is a dimensionless, delta H is the elevation pressure. Average T is the average temperature, P average is the average pressure, Z average the average compressibility factor at P average and T average, and L is the length of pipeline, whereas 1 upon F square root that is the transmission factor which is dimensionless. So, on taking all constant as a C, so the previous equation becomes QB is equal to C P1 square minus P2 square minus 58G delta H P average square upon RT average Z average whole divided by 58 Z average T average GL 1 upon F d to the power 2.5. Now, if the pipeline is horizontal or delta H is insignificant to compare the value of P1 square minus P2 square. So, P1 square minus P2 square is greater than 58 G delta H P average square upon R T average Z average. Then the elevation term is omitted and the final equation becomes QB is equal to C P1 square minus P2 square upon Z average T average GL 1 upon F D to the power 2.5. So, this equation shows the effect of transmission factor and the diameter of the pipeline on flow of gas in pipeline. Now, in this particular segment, we discussed about the design equations and especially the impact of kinetic energy, potential energy, friction terms, etc. For reference, we have enlisted a reference for your convenience. If you wish to have further reading, you can take the help of this particular reference. Thank you very much.